The third talk for today will be given by Stephanie Novo. Is she here?
Oh, yes, right
I
here.
lost her. Yeah, okay, perfect. She's an assistant professor in the Department of Psychology and the Department of Bioengineering and the Center for Cognitive and Brain Health at the Northeastern University. In her work, she focuses on creating tools to facilitate more precise human neuroscience inference and prediction. Her research lies in the intersection of data science, neuroscience, and open science. Specifically, her work has addressed open questions and introduced new paths forward to facilitate more reliable and valid neuroimaging research and paves the way towards improving individual-level model of behavior and disease. Previously, she received a BS in Chemical and Biological Engineering from Princeton University and a PhD in the Interdepartmental Neuroscience program at Yale University, and completed her postdoctoral training at the Radiology and Biomedical Imaging at Yale. Today, her talk is focused on mapping the landscape of effect size in fMRI, insights from large publicly available datasets.
All right. Well, thank you so much. I'm glad to be here today with MRI Together and also with the Brain Hack. We have a Brain Hack Northeastern happening right now at the same time. So thank you in-person people and people across the world in MRI Together for being here. So I know our whole symposium is about the reproducibility crisis, and I just wanted to start off with this slide that I like to start off with to just see what people think about whether you think there is something of a reproducibility crisis that our field, let's say human neuroscience, has been experiencing recently. So just raise your hand if you think there might be something of a reproducibility crisis. All right, so in the room, that's pretty much the majority of the room, although as usual, there are a few hands that abstain. And actually, there was this survey done by Nature of biomedical scientists asking whether they felt like there was something of a reproducibility crisis. And actually, the majority of scientists did feel like, even if the word crisis is a little bit overblown, there are at least some really major problems with reproducibility in the field. And we've seen this kind of echoed throughout different types of agencies and even in industry. So when we write grants, we might have to write a rigor and reproducibility section now. NIH has been trying to get us to improve reproducibility in their funded work. Amgen actually published a paper also about trying to raise standards in preclinical cancer research. And there are other companies that were thinking about similar problems. And also in neuroscience broadly, we've been talking about issues with reproducibility, with power that's really endemic across the field. And we've been talking about this in neuroimaging as well, specifically. Well, one big solution that people have been talking about is a need for more precise analytical methods. People have thought maybe some of our better methods, more powerful methods, more precise methods can help us deal with our historical issues with having very low power and low reproducibility. So when I think about precision, I think of these measurement theory concepts that underlie having accurate measurements. So we think of accuracy as being built upon the cornerstones of reliability and validity. By reliability, I'm referring to the ability to get similar results given repeated trials. And for validity, we're talking really about the correspondence with some desired outcome. So as an example, if we have this target that we want someone to shoot at, and we really want to hit the bullseye, let's say they shoot in this pattern. We can see the arrows are pretty well clustered together, so it's pretty test retest reliable in that sense. But it's not really hitting the bullseye. So if we care about, actually hitting the bullseye, we would say it's not actually corresponding with our desired outcome. If instead we found that someone shoots in this pattern, we can see that the arrows are more spread out one from another. So we'd say it's not quite as reliable as the previous context. But if we took the average, the Euclidean average of these arrows of the points on this target that are hit, we might see that it converges upon that bullseye. So in this sense, if we took the average of all of these measurements, we might actually get correspondence with a desired outcome. So these are just a couple examples of where you can have something that seems reliable but not very valid, or valid but not reliable. And you can see how both of these might be pretty helpful. Even if this case is fully valid, any individual shot is not going to be likely to hit the bullseye. So I'm going to skip over reliability a little bit here. This is a topic I often talk quite a bit about in other talks. But if you'd like more of a guide to some principles of test-retest reliability in neuroimaging, please check out this paper. And we also have Alex Fischbach, a PhD student in my lab, who've been investigating this in the subcortical context. But here I'm going to dig a little bit more into validity. So our correspondence with a desired outcome. And specifically, I'm talking about validity of our inferential methods with the standard goal of wanting to find true positives that exist and limit false positives. So there's been a lot of discussion specifically on this finding true positives point about how we might be able to improve power in fMRI. Many different papers suggest many different things. So some people suggest that we need adequate sample sizes or more reliable and valid measures or more powerful inferential procedures, more powerful study designs. But actually, although this is kind of a movement in the right direction, it actually raises many more open questions. We need adequate sample sizes. Really, how big is big enough? Is it consortia level, as some people suggest? Is it smaller? Is it larger? What are our benchmarks for saying that something is actually reliable enough or valid enough, etc.? And answering all these questions actually requires us, if we want to improve power, it requires us to have an ability to estimate power that's specifically tailored for neuroimaging. And this is deceptively difficult. So here I'm going to talk about a path towards better estimation of effect sizes and subsequently power for better study planning in fMRI, and also for benchmarking all these techniques that we want to benchmark. The first step of this is to understand what sort of effect sizes we might expect for typical study designs. And then once we know what sorts of effects we might expect, then we can develop on top of this some tailored power estimation procedures for typical studies. So let's look at this step one. First, we're going to start off with some typical studies. So we're using large publicly available datasets to help us define some of these studies. And here, when I say study, I'm referring to an analysis, a unique analysis to estimate the effect of a unique phenomenon in a given dataset. So a single dataset might comprise multiple studies. And the criteria here is I'm looking for large data sets. We're trying to get as accurate estimates as possible. We're also measuring the accuracy with which we can detect these effects. So we'll quantify that explicitly as well. But to start off with, we want to start with large data sets that seem to reflect typical study designs. So we start with 6 data sets at the moment, which reflect 4 different sample sizes, ranging from 400 to actually 35,000 in the UK Biobank, a really great resource for those who haven't encountered that before. 2 brain mapping types. So a smaller proportion of what we're going to show here is from activation mapping. The rest will be from functional connectivity. 3 effect types. So we have correlations, we have 1 sample t-tests, and we have 2 sample t-tests, which are very commonly done in the field. And then 5 outcome categories, ranging from biometric, cognitive, psychiatric, and more. So in total, we have 45 studies leading to 45 effect maps. This is actually still growing. We are actively recruiting contributions to this power calculator, to right now the effect map, effect size explorer. So we have more and more studies than this at the moment, and there will be more in the future. But this is a snapshot of what we have so far. So that's the data that we're starting with. We can take this data and we can take the studies that we're identifying from this data, and we can estimate effect sizes from this. So to start off with, we're going to convert everything to Cohen's d, just because that's the most common measure of effect size that we do see in neuroimaging, and it allows us to compare across different types of studies and across different types of designs. I'll also mention that we are also estimating R-squared. That's another really common effect size measurement used in psychology. And then we will estimate the sample sizes needed to detect different effect sizes. And I just want to say, kind of as a rule of thumb, we have, I won't move too far away from the screen, but we have for 3 different Cohen's D's that are sort of the typical rule of thumb that's been developed by Cohen. There's actually different numbers of subjects that are needed to detect these for within subject designs versus between subject designs. So there's already something that's kind of limiting our ability to compare directly between, let's say, a one sample t-test and the results from a two sample t-test. Namely, if you have 400 subjects per group, so 800 subjects in total, and you do within a between sample t-test, you need twice the subjects as if you had 400 subjects in a single group for one sample t-test. So just keep that in the back of your mind. We're trying to make things as comparable as possible by using some common effect size measures, but there are still limitations in how we can compare everything. So we can look at a few standard sort of typical results from this. And I'm going to quantify some 95% simultaneous confidence intervals for these effect sizes. So what that means is that we expect that the true effects across every part of the brain will be within these confidence intervals if we did in 95% of possible experiments that we did. So we're hopeful that, most of the effect sizes that we report are somewhere within these confidence intervals across the brain. And I'm doing this because we're doing this across all edges or all voxels in a given experiment. So here are some representative studies from the HCP. Here's a between subject design. This is a correlation between some brain measurement and behavior, here functional connectivity and behavior, and here we're looking at age. This is what might be called a brain-wide association study, commonly in our field. Here you can see that the simultaneous confidence intervals, and I'll just give a little bit more of a background to this figure. Keep wanting to step away, but I think I should be here in the video too. On the x-axis, we have all of the edges. So a functional connectome is made up of many different edges in a graph. And we've sorted all the edges in the x-axis by their effect sizes in the y-axis. So the y-axis is the effect size in Cohen's d. And you can see that these simultaneous confidence intervals tend to overlap with 0. So we can say sort of conservatively, we wouldn't be able to, it's possible that each of the edges in this particular analysis could have a 0 effect size. It's trivial null, probably not exactly 0, but it's hard for us to say that it could be non-zero. If we do a two sample t-test, however, here we have biologically female versus biologically male functional connectivity contrast. We see that we could have a few more effects that could be non-zero. And then when we move to within subject analyses, here we have a one sample t-test, just the connectome during a working memory task compared to rest. We can see that there are many more effects that could be possibly non-zero. And then also in the activation mapping context, we also see more effects that could be non-zero, although we see fewer of these than we see with the functional connectivity context. Overall, some patterns here, we tend to see that these one sample t-tests, these within group designs, tend to yield larger effect sizes than these between group designs. And we tend to see functional connectivity being a little bit, having stronger effects than activation mapping. So we can take these representative effect maps and we do this exact same analysis across all the different studies that we have in the database. And we see this same pattern. So I would say, to be most conservative, it makes sense to plan for most effects to be quite small for between subject analyses. And actually, to be conservative, you might expect some of them to perhaps be very close to 0. We find that psychological constructs tend to be most difficult to detect, and our maximum conservative effect size tends to be, so if I'll step back and say our conservative effect size is kind of like, what is the smallest effect size that's within the confidence interval? So if it overlaps with 0, our conservative effect size would be 0. But if the whole confidence interval is just outside of 0, we take the part of the confidence interval that's closest to 0. So across all these studies, the very largest effect size that we observe, that we consider conservative for between subject analysis, is still less than medium. So we still don't see, large effects, even the largest possible effect that we could look for. For the within subject context, however, we can see that effects could be potentially modest to medium. So there's more non-zero effects. And we do see that the maximum conservative effect size is actually larger than that Cohen's d threshold of 0.8, which is thought of as a large threshold. So here's just a little chart of what you would need to detect the maximum conservative effect size for each category, from the correlation to the 2-sample t-test to the 1-sample t-test broken out for functional connectivity and activation mapping. So detect if you happen to magically know what part of the brain had the very largest effect. For a brain-wide association study, you would need about 400 subjects per group. Whereas for an activation mapping study, if you knew the single voxel that gave you the largest activation, you might need only 5 subjects. And correspondingly, we can get much larger power for certain ones of these design contexts compared to others. Of course, that's, best case scenario if you happen to know beforehand exactly where to look, but it does give us kind of a sense of how lucky you could get. So we have a Shiny app that we've developed to allow researchers to explore these effect size findings. We think of this as kind of a first step for maybe doing a standard power analysis. I'll talk a little bit later in the future about some power analysis plans that we have. But also other researchers who might be developing computational methods could use these effect maps as priors for their analyses or other sorts of information for analyses that they might do. So here, I know it's blocked off on the Zoom, but I'm going to have Hallie Shearer come up to the front. She's an RA in the lab who's been working really hard on developing this app. Sort of describe it to you.
Hello, I'm Hallie. I've been building this app and I will walk you through it a little bit. So this is our Shiny app, and if you haven't heard of a Shiny app before, we don't call it that because it's sparkly or anything. That's just because that's the name of the package that we use to build it. It's in R and the Shiny package. So there's a QR code in the top right corner that I think is blocked by, it might be blocked for you, but if not, you can use that to go to the Shiny app, but I will warn you, oops.
I'm just going to move it out of the way. Sorry.
Yeah.
So people can
One second.
online and in person.
There we
Okay.
go. And then I'll move myself out of the way.
Excellent.
Okay, there we go. So you can use that QR code to go to the Shiny app, but I will warn you that we haven't really tested the scale of this. And so if everyone goes to it, it might crash. But if that happens, you can go later and check it out afterwards. But if you do make it to the app, then this is what it would look like. So like Steph said, the goal of this is to be able to explore those effect maps and sort of summarize them in a meaningful way and see where they're located spatially in the brain. So all of the studies that we have from the database are shown on here in the middle, and you can filter through them to get ones that are more similar to what you're interested in by using the different options on the left here. So you can filter them based on the data set. If there's a certain data set you're interested in, maybe if you're interested in studying children, then you choose the ABCD data set. You can constrain the map type, either connectivity or activation maps. And then the task would be whether they're at rest in the scanner or doing an emotion task, a social task, that sort of thing. And then you can select just certain tests, so brain behavior correlations, the 1-sample t-test or the 2-sample t-tests. And then in terms of spatial scale, this screenshot's not perfectly updated. So we have some stuff that we're about to deploy to the Shiny app probably within the week, that we have univariate, where you can see the effect size for every single edge in the study, or you can do pooling. So that's before the analysis is run, we pool the data within each network, and then you only have 10 networks that you're studying instead of 37,000 voxels, or I think even more than that. So you can have pooled data or univariate, and then we also now have multivariate analyses that maybe Steph will talk about a little bit later. They're a bit complicated, but we include those as well. And then we also have motion regression that's not shown here yet as well, where you can look at the results if you don't account for motion, and then if you regress it out, or if you do thresholding to account for motion. So that will all be available very soon. And then the last thing on the left there is grouping the results. So rather than showing every single study in the middle there, you could group them by statistic. So you'd see one plot that's the average of all of the brain behavior correlations that you've seen, or that fit the criteria. Or you can group it by behavioral phenotype, or there's lots of options there. So that can kind of help you summarize across the different studies. So in the middle and on the right, then we visualize these effect maps. So in the middle are the same plots that Steph was showing you before. And mainly these are helpful for seeing like what proportion of the voxels or the edges are potentially not zero. So I've colored them slightly different from Steph. We have red if the intervals overlap with 0, and green, you can see a little bit of green there for the intervals that don't overlap with 0. But this doesn't tell us where they're located, so that we look at on the right. So for functional connectivity studies, this is showing pretty much a functional connectivity matrix, but instead of the correlation values being shown, it's the effect sizes. So you can see here, for example, this blue box is showing you that there's more negative effect sizes within the primary visual cortex. Then below, that's kind of cut off here, but you would see if you go to the app, we also have activation maps. Actually, I think on the next slide, you can see that better.
Oh, yes, sorry, I think I took over.
That's okay. This should work.
Excellent.
Okay. So yeah, on the right-hand side here, we can also visualize those effect maps on the brain. So you can get an idea of where there's some hotspots here with bigger effect sizes. I'm not going to walk through an example because last time that crashed with people on it, but feel free to explore it afterwards, and we're open to questions if you have any. Now I'm going to take a couple steps back and just explain how we got to this app. How are we doing for time? Yeah, just for a couple minutes. So we start with the subject level data that we get from contributors. Like Steph said, if you have a large data set with more than 400 people, we would love to chat with you about including it in the app. That we need subject level, either connectivity matrices or activation maps. And then also something about the subjects that we can use to create a test. So for example, you could give us every subject's age, and then we could do a brain behavior correlation with that. So for every study that we can do, we do the analysis to get the statistical maps, and then we turn those into effect maps by converting them to Cohen's d, like Steph mentioned, and then we congregate those and feed them into the Shiny app. And the Shiny app is quite simple. It's really comes down to this one app file that's an R script, and it has two parts. There's one that codes the user interface, so that's saying like put a plot here and put a button over here. And then the server part, the second part, codes for the interactivity of that. So you'd say when someone clicks that button, here's what to do. When someone makes a selection with the button, update the graph like this. Then there's a data directory that just has all the data that the app needs, including the effect maps and any sort of plotting data, and then some helper scripts and another R file. So it's quite simple to make the Shiny apps. Would recommend giving it a try for exploring some data. And I will pass it back to Steph.
All right. Thank you, Hallie. And Hallie and I gave a lot of thought to this contributed data format. We went back and forth a lot. And I know that there are some open discussions in the field as well about how we should contribute, statistical maps or intermediate results as well. But for us, we think that this is a nice way to contribute subject level statistical maps that can then be ingested by a number of different apps and used for different types of purposes. We even infer the test type. I know Hallie worked really hard on that, inferring what sort of test type based on some really simple information that's really easy for a user to provide. All right, I'm going to go back to playing this. All right. But just so you know, there are two ways you can interact with this. You could contribute us data, but you don't have to. You can just go to the web app and click and point. So very quickly in like a minute and a half or less than, I'll say there are some historical procedures used for estimating power. Some of them are no longer available. I think most of them are no longer available, but also they tend to rely on parametric inferential procedures or for people to provide maps. But we are developing a power calculator that will circumvent some of those limitations, where all you have to do is provide a few details about the study you want to collect, the study you want to conduct, and then we'll go through the database and we'll provide a best sort of benchmark recommendation on what sort of power you might expect to detect an average effect there. And that's Fabrizio Cravo is a postdoc in the lab. He's working hard on that. Yes, so in summary, you might want to plan for considerably smaller effects for between subject designs, noting that there's some differences in the types of studies you might run in if you're doing typical sort of fMRI research. Large open data sets and empirical benchmarking can really lead us towards practical guidelines. That's, I think, a really important, actually a critical trend that's been happening recently in the field in neuroimaging. And I would also highlight, we tend to see better, more reliable and better and highly better powered effect when we use broader scale and multivariate procedures. So I think that that's something that people can strongly consider. I think it also tends to match the scale of the data that we're working with. Joshua Curtis and I wrote a paper about this, talking about, thinking, reconceptualizing, broader scale types of effects. But please check out the app and feel free to contribute. Couple tools. Thank you to the lab, not only for all their work for BrainHack today, but also all the work that I'm showing today, and contributors. All right, thank you.